There is a protection mechanism. So here the protection mechanism is covered in a very nice way. So unit number 3, multitasking. So let's start from the basics of multitasking. Now task is basically the collection or is a program routines that perform a specific function. So this is what is called as process, or same is called as task. Now what is multitasking? Multitasking is basically a feature of 8036 processor in the protected mode that allows execution of several programs simultaneously. So there is one example that you might have observed while performing some work on PC. Suppose you are doing some work on PC and by that time you have made the video player on. You are watching some movie clip on your PC. Side by side you are running MP3 player on your PC, and also you are doing some work, some typing work basically on Word, and also you are doing some work in Microsoft Excel. So all those four tasks are running, and here microprocessor will give some time to execute the video application. After that, some time, let's say 5 milliseconds, will be allotted by the microprocessor to run the MP3 related application. Then next 5 milliseconds will be allotted by the microprocessor to execute Word related application, and for next 5 milliseconds microprocessor executes the Microsoft Excel related application. So here for some time video, then MP3 player, then Microsoft Word and Excel, all those are running on this time shared basis. So in time shared system, the program control switches from one task to another task after fixed interval. So here, though the processes are executed one after other in time shared manner, the 8036 microcomputer system behaves such that all the tasks are simultaneously being executed. So here you will feel like each and every task is getting executed at a time, but the switching is so fast that you will feel each and every task is getting executed at a time, but basically each and every task is not getting executed at a time. Here each task will be given some time, and during that time the task is getting executed one by one. So this is what is called as multitasking. So your microprocessor is switching from one task to another task very rapidly. A task is invoked by an interrupt, exception, call, or jump. So a task can be called by other tasks by using interrupt, or by using exception, or by using call, or even jump can be there. The 8036 microprocessor supports task management data structures that are used for multitasking in the protective operation. These task management data structures are task register, task state segment, task state segment descriptor, then task gate, then task gate descriptors. In order to have this kind of switching in protected mode, means in order to have efficient multitasking in protected mode, we will require those task management data structures. So with the help of this task management data structure, we can have multitasking in a protected way. So how does it happen? That we will see. Now there can be two things. You might be knowing procedure switching. While working on C programming, you write a main program, and after main program you write functions. So those functions are the procedure. Suppose procedure A is procedure means function A, procedure B is function B. So you are having this main program, and from this main program, let us suppose those functions are being called. So in this scenario, this is called as procedure switching. Whereas in case of task switching, you are having a program. So within that program, there are a set of programs. So each set of program is called as task. And here, the task is being called. A task is calling to some other task. It may be interrupt task or it may be exception related task. So there are two scenarios now. First one is procedure switching, another one is task switching. So let's see what happens during procedure switching and what happens during task switching. So here, in case of procedure switching, microprocessor saves less procedure state information. Whenever switching occurs, means let us suppose here the procedure A is being called after instruction C. So your microprocessor will jump to this location, and after ending this function or the procedure, the microprocessor will come back to the next instruction. So during this switching operation, microprocessor saves some information. So less processor state information basically will save during switching. Okay. So those can be contents of general registers, means GPRS, general purpose registers. Those can be the content of EIP, that is instruction for flagged registers, and it can be a return address. So return address can be the pointer. So all those things will be pushed, and while return back, all those things will be popped out. Whereas in case of task switching, when one task calls another task, during that time, it will have to save more processor state information. So lots of information will get saved during switching, and while coming back, the microprocessor will pop out the saved information. That we will see later on. Now we are working in a protected mode. So whenever task switches from one to other, lots of processor information will get saved, and along with that, lots of protected mechanism related checking will be done. Now, in case of procedure switching, a procedure call pushes the contents of the saved register onto the stack that we have discussed right now. All those things will be saved onto the stack. Whereas in case of task switching, task pushes the contents of the processor state information is saved into TSS. See, whenever procedure switching happens, during that time, microprocessor saves this information onto the stack. And whenever in task switching happens, so during that time, here lots of information is available which is to be saved onto the stack. So for that purpose, microprocessor uses TSS. It is task state segment. So in this task state segment, it is one of the type of stack, but to save more processor state information, microprocessor uses TSS. So all those information will be saved here onto the TSS. Now a procedure can call itself. It is said to be re-entrant, means the same procedure can be called again and again. So whenever same procedure is being called, so in this scenario here, the context related to the same task will be saved again and again. Now here, during task switching, the tasks are not re-entrant because already lots of information is to be saved. So all those information will be saved again and again, again and again. If this scenario happens, if those are re-entrant, then lots of memory will get consumed. So here, tasks are not re-entrant. Once the task is called, then task will have to complete, will have to return back. Then and only then, the next task will be called, or the same task will be called after completion of the task. So this is the discussion related to procedure switching and task switching. All of we know the procedure switching. Now we are learning task switching. So it was the comparison in between those two. Now let's switch over to the next topic. Now let's see TSS, that is task state segment. So all of we have discussed right now. In case of procedure switching, microprocessor uses stack, whereas in case of task switching, in order to save lots of information related to task, microprocessor uses TSS. So here, context of new task and old task both are saved into the TSS. Means whenever task switching happens, so from this task to this task, and from this means new task to old task, back again. So it is old task and this is new task. So the context related to old tasks are saved onto the TSS. When switching happens, the context related to context means the processor state information will be saved onto the TSS, old TSS. In the same way, the context related to new task will be saved onto another TSS. So this is new TSS. So we will require two TSS in order to save the context or the processor information related to the task. So here, whenever switching happens, tasks require TSS, task state segment. So here, for the new task, the data and information needed is collected and loaded. However, this information is not loaded onto the stack. This information is stored in a special memory segment called as task state segment that we have discussed right now. Size of TSS. The total overall size of TSS is 104 bytes. 104 bytes. How do we know that it is of 104 bytes? So if you do 26 into 4, you will get 104 bytes. So there are total 26 location, and in those 26 location 4 bytes are saved. It means that, suppose let's take an example, the 0th location address, it contains total 1, 2, 3 and 4. There are total 4 bytes. So each location contains 4 bytes. There are such 26 locations. So if we try to count all those locations, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 and 26. There are total 26 locations and each location contains 4 bytes. So 26 into 4, it is 104 byte. That's why it is 104 byte long. So TSS is of 104 byte long. The task state segment, that is TSS, comprises the storage areas for all of the 80386 microprocessors 32-bit registers. So microprocessors 32-bit registers will get copied into this area. Okay, and the 16-bit segment selectors. 16-bit segment selectors. It also contains additional storage for stack pointer and segment selector. Stack pointers and segment selectors. For each protection level of stack, for each protection level, stack pointer and segment selectors are there for each protection level. So you can observe over here that the stack pointer related to protection level number 2, protection level 1, protection level 0 are present, and here the segment selectors for protection level 2, 1, 0 are present. So here in TSS, the processor saves the various registers within the segments, that is all 8 general purpose registers. So those are the general purpose registers along with the segment registers. EIP flag register, that is E flag register, CR3, that is control register 3, and privilege level stacks. Privilege level stacks means those are stored in TSS. The main purpose of saving CR3 means control register 3 is that the CR3 contains the address of the page directory. Page directory can be changed for each task. Similarly, we have the LDT that can change on as per the task basis. So here, as task changes, the LDT can be changed, and to locate the LDT we will require this CR3. The field marked with T at this location is used for enabling or disabling the task switch trap. If this bit is set, then 80386 performs a task switch normally. If this bit is clear means 0, the trapping of task is disabled. The IO permission bitmap, which is present at this place, is used for IO protection, and the backlink field at this place you can see it's the offset in the TSS00H over here. It keeps a track of the task chain. Once the task finishes execution, it uses the backlink field to return to the previous TSS. Means if these task switches happen, so in this case, this is the TSS of this old task and it is a TSS of new task. So here there is a backlink information. So from this backlink information, task will come to know that the return address is over here. So this backlink information is available. So with the help of this backlink information, this task will come to know to which TSS it should go, and this TSS is related to this task, that is task number 4. So in this way, the task A will come back to the main program's task number 4. So as soon as 80386 starts executing the new task, it reads the information that is present in the first 104 bytes of the task TSS. Most of the data is copied as it is, and the execution start using CSEIP of the new task. So it means that whenever task switching happens, the old program will copy its context on old TSS, and the switching happens, and during that the new task will be loaded with new TSS. And here there are some fields which remains constant, and there are some fields which gets changed as task get changed. So here in this scenario, the dynamic fields are those fields which gets changed as per the task switches. So those dynamic fields are EAX, ECX, EDX, EBX, ESP, EBP, ESI, EDI. All those are the dynamic fields. Those segment registers are also dynamic field. Then flag register along with this EIP. All those are dynamic fields. So the processor gets updated with each task switch. Static fields are those fields which will remain constant, that is IO permission bitmap, then T bit, then PDBR field of CR3 and the LDT. Now let's see what happens during multitasking. The 386 microprocessor transfers execution to another task in any of the 4 cases. So the current task, if it executes jump or call instruction. So if there is a jump or call instruction which is getting executed, so let's suppose call instruction has got executed, call some exception related task, then it will jump to that particular instruction or exception and will come back. So the current task will jump to the new task when it executes jump or let's say call instruction. This jump or call instruction can happen in a two way. So if jump or call get executed, it will get executed by or with the help of TSS descriptor, or it can get executes to task get. We will see the TSS descriptor and task get descriptor later on. And the microservice transfers execution if an interrupt or exception indexes to the task get. And the fourth scenario is the current task executes an irate, that is return from interrupt, when NT nested trap flag is set. So the fourth scenario is this scenario, or we can say the fourth scenario is applicable over here also, like the execution of irate. The current task executes an irate. So if this task executes irate, the switching also happens. So those are the four scenarios. Whenever task switch occurs, 80386 automatically save the contents of the old task in a TSS and loads the context of new task specified in another TSS. This we have discussed already. So now students, we will study what happens when jump and call instruction is executed. Before this we have discussed what happens when or in which condition the microservice transfers execution from one task to another task. Now we will see what happens when jump and call or task switching happens. So firstly, whenever jump or call instructions are gets executed, so those gets executed. So firstly, Microsoft checks the current task is allowed to switch to new task or not. So firstly, privilege level will be checked. Firstly, Microsoft checked whether the current task is allowed to switch to the next task. If yes, then next time on the second step, Microsoft checks the TSS descriptor of new task is marked present and is it valid. So TSS descriptor basically describes the TSS. That is the simple definition of TSS descriptor. So firstly, microprocessor checks TSS descriptor is a data structure in which the information related to the TSS of new task is stored. So microprocessor checks the TSS descriptor of new task, means checking of this is done, and is it present in the database and is it valid. If yes, then save the state of current task in current task TSS. So this descriptor is present, and if it is valid, then what happens is the microprocessor saves the context or the important information related to task in this TSS, and it is pointed, this TSS is pointed by this TSS descriptor. Then load task register with the selector of new task descriptor. So we have got the TSS of the new task. Then the task register is loaded with the selector of new task descriptor. Means now this descriptor should get located. So that's why we have task register. Task register is a register which points to the TSS descriptor of the new task. So in this way we have got the TSS, and we have, that is the microprocessor have saved the important context register into the TSS. Then what about the current task or the old task? So here Microsoft loads the new task step from its TSS. So here it's having its own TSS. The current task will get loaded with the TSS and the execution continues. So to cause task switch, a jump or call instruction can transfer execution to either a TSS descriptor or task task get, the effect is same in both of the cases. Now we have discussed that what happens when task switches from one task to another task and related to its TSS. Here the situation is not so easy. Now to have all those things, to execute all those things, microprocessor also goes through the privilege level checking along with all those things. So how that privilege level checking is done, that we see now. Now just before studying the protection level checking during task switching, we will just go through the basic of privilege level checking. This is in the chapter first of unit 3, or the first part of unit 3. Now here, what do you mean by CPL? Because for privilege level checking we will require three fields, that is CPL, then we will require DPL, and we will require RPL. All those three fields are checked, and then decision will be taken whether the code or the task is able to access the data or not. All of we know that those protection rings. Here there are four privilege levels in which the program executes. So highly privileged are the operating system kernel related program. This is level 0 privilege level. Privilege level 1 contains operating system related program. Privilege level 2 contains the services related to device drivers, etc. Then privilege level 3, which is having lowest privilege level, those are the application software, just like we have discussed VLC media player, Excel, Word, MP3 player. Those are the application user applications. Now here, whenever the code runs in a code segment, all of we know that code segment holds the code, and the CS register holds the base address of the code segment, and this code segment or the code inside the code segment is having privilege level, so it can get executed at privilege level 3, 2, 1 or 0 depend upon the code. The CS register, that is code segment register, which holds the base address of the code segment, is having one another field. This is called as cache register. So this is the hidden part. So in this hidden part there are 2 bits of CPL. The lowest 2 bits of CS segment register hold the current privilege level, that is CPL. This is the privilege level of the program being run. Actually, the CPL is the privilege level of the code segment from which instructions are being fetched. So from this code segment, the instructions gets fetched and gets executed by the execution unit. The CPL changes when control is transferred to code segment with different privilege level. Suppose the task switching happens. So let us suppose the program running at level 3 are calling the programs which are running at higher privilege level, that is privilege level 2. So in this case the CPL related to this task and the CPL related to this level or this task will get changed when the transfer happens. Now this is the discussion related to CPL. So from this discussion you might have got an idea of what do you mean by CPL and how it plays an important role while task switching. Now let's see DPL, that is descriptor privilege level. It defines the privilege level of the target segment. This is used to control access to the segment using the protection mechanism. So this is DPL field, it's of 2 bits. This DPL field basically the descriptor privilege level, it defines the privilege of the target segment that we will see later on. DPL is the field inside the descriptor. So when we study TSS descriptor, from this we will come to know what we mean by DPL. Then there is requester privilege level, this field available in the selector or the segment selector. The segment selector contains a field called requested privilege level, that is RPL. The RPL is intended to represent the privilege level of the procedure which creates the selector. So this RPL, DPL and CPL, those are used for checking the privilege level. Now we will see multitasking, that is task switching without task gate. So here all of we know that whenever a task switch occurs, 80386 microprocessor automatically switches, or it 80386 microprocessor saves the contents of the old task in TSS and loads the context of new task in another TSS. So here the new TSS can be identified. The new TSS can be identified using a TSS descriptor, which is referenced through the task gate. But there is some problem, that is 80386 is not aware as to which TSS to save the old state, and hence the task register is needed. So here task register is needed to save the old state in the TSS. The selector of the currently running task TSS descriptor is always kept in a TR. So here the task descriptors selector is there in the TR register. The task register is functions to point to an index pointer into the GDT to locate the TSS descriptor. It means that whenever task register is loaded with the selector, that selector will locate the TSS descriptor. TSS descriptor is the data structure like this. Previous to this we have studied different descriptors. So this is the descriptor which selects the TSS, that's why it is called as TSS descriptor, and this TSS descriptor is located by the selector field of the task register, and those TSS descriptors are kept in the global descriptor table inside the 80386 memory. The size of selector is of 16-bit. The task register contains two parts. One is visible part, means this one, selector field, and another one, that is base address and limit field. Those are invisible to the user, means user can program task register. He can use some instructions to load some value in the selector so that TSS descriptor will get selected, and there is an invisible part attached to the visible part of this TR. This is not accessible to user. So the invisible part is automatically loaded with the information associated with TSS descriptor. It means that if you see this TSS descriptor, this TSS descriptor is having limit field, limit 0 to 15, and the remaining part of limit is there in 16 to 19. So limit field is of about 0 to 19, means total it's of 20 bits. So the TSS descriptors limit field 20 bits inside the limit field will get copied into the limit of task register's invisible portion, and it's having base field 0, then 23 to 16 and up to 31. So 0 to 31, total 32 bit of base field is there inside the TSS descriptor. So all those 32 bits will get copied into the invisible part of task register. So this limit and the base, both the field will get copied into the invisible part of this task register. Whenever new task begins, TR is updated to hold the selector of the new task descriptor. So whenever task switching related instruction, that is call, etc., gets executed, those instructions are having selector field and offset within it. So whenever those kind of instructions get executed, at that time the selector associated with it will get copied into the selector field of task register. This selector field will select the TSS descriptor. These TSS descriptors, two fields, that is base field and limit field, will get copied into the task register cache part, that is invisible part of this task register. All those fields means both the fields will get copied into the invisible part. This is also called as task registers cache field. And from this field the TSS segment's base address is located and limit is of 20 bit. How much long is that TSS is, that is been defined by this limit field. So with the help of base and limit, the TSS inside the memory will get located. Now task switching will happen, because once microprocessor is having TSS, now the context of new task will get loaded in this TSS. So here all those things are done, means here those things should be done to select TSS, and with the help of those things we check privilege level. Once privilege level is checked, we get the TSS, then context of the task will get saved into the TSS, and then actual switching will happen, or the new task will get executed. Now the question is, why to put the base and limit field of the TSS in the cache part of this task register? The answer is, as the base and limit value is kept in the invisible part of the task register, the task execution becomes very easy and efficient. This is because the processor need not to repeatedly fetch the values from the main memory when TSS of the current task is referred. Now, whenever again the same TSS descriptor is located to locate the same TSS, so in this scenario the microprocessor doesn't go through all those steps. Microprocessor is having this base and limit values in its cache register. So microprocessor will jump directly on this field. Once microprocessor know those two fields, directly the TSS will be loaded. Now at some point of discussion we have discussed that the selector part of this task register can be programmed. For that there are two instructions. One is LTR, that is load task register. This is privileged instruction. And one more instruction is STR, that is store task register. It is also used in protected mode. It is basically a not privileged instruction. So when all instruction get executed, the selector is loaded into 386 processor's task register. So selector is loaded in the selector field of task register. Then the corresponding TSS descriptor is taken from GDT. So corresponding TSS descriptor is taken from global descriptor table. Then TSS descriptor is loaded into task register cache over here, and from those fields the TSS of the task will get located. So this is the summary of the discussion. All this process happens only when X is write information, that is the information related to privilege level. Access write information of the descriptor is satisfied. So which is the access write information? CPL, RPL and DPL. Those fields are needed to check, but along with those fields there is some information which is also needed to be checked. So firstly, P bit inside the descriptor, that is this bit, is checked. So it should be 1. It means that the descriptor is present. the descriptor associated with the selector or the instruction is present. Then the second one, the called task, and this is the main task and this is the called task. This task should not be busy, therefore this b bit should be 0. It means that task is not busy. If task is not busy, then task can be switched, and the CPL must be equal to DPL. It means that the instruction, this particular instruction which is getting executed in the data segment, the privilege level associated with the data segment is CPL. So the privilege level associated with the data segment, that is CPL, must be equal to the DPL field, means this one. So all those checks will be done related to TSS and the instruction. And after checking all those things, the current task is allowed to switch to the desired task. So all those fields will be observed and it will be checked against this. Here CPL and RPL will be checked. So CPL, all of we know that CPL resides in the invisible part of the CS register. It is associated with the instruction. So CPL will be checked against the RPL. RPL is there in the selector field. Okay, so it's of 2 bit. So RPL will be checked and CPL will be checked. Maximum of CPL and RPL should be less than, it should be less than or equal to the DPL field inside the descriptor. It means that this field of the descriptor. If this condition is satisfied, then and only then the current task is allowed to switch to the desired task. Students, up till now we have seen what happens inside during task switching without task gate. Means the selector field of task register will get loaded, it will locate TSS descriptor and this TSS descriptor will select the TSS. Now we will see what actually happens when a current task is getting executed and when what happens when the current task switches to the new task. So what the things happen, which checks are done by the microprocessor, which things are loaded by the microprocessor during task switching. So here when task switches, the status of the current task is checked in order to see whether it is permitted to switch to desired task or not. It can be obtained by checking the DPL of the desired TSS with RPL and CPL of the current task. So if maximum of CPL is and RPL is less than or equal to DPL of the new TSS descriptor, then and only then the current task is allowed to switch to the desired task. If this check is false, then switching will not be done. So let's suppose here this condition is satisfied, that is the first condition. Then TSS will be located, sorry, TSS descriptor will be located. Just before locating the TSS descriptor, the microprocessor checks whether the TSS descriptor of the new task is present or not. Means this TSS descriptor is present or not, it will be checked. If it is present and the task is not busy, then microprocessor saves the state of the current task in current task TSS, because if TSS descriptor for the new task is present and task is not busy, it means that it has now located the TSS of the new task. So here Microsoft save the state of the current task in the current task TSS, and then load the selector of new task in the task register which point to the new task TSS descriptor, and then load the task state in TSS, that is new TSS, and continue the execution. So here in third scenario, the context of current task will be loaded in TSS, and in fourth scenario or the fourth step, the selector of new task is loaded in the task register which will point to the TSS descriptor, and then this TSS descriptor will select the TSS of the new task, and then load the new task state in the TSS and continue the execution. So here the execution will get continued. Here in the fifth state, the new task has already saved its context into TSS. After the execution of this new task, just before returning to the old task, here new task TSS has old task backlink information in the backlink field of the old TSS. This backlink information is automatically loaded into task register. So this backlink information is automatically loaded into the TR of the old task. So in this way, the new task switches, or it gets an address where to switch. Okay, so old TSS get activated. This TSS will get activated and resumes the program at the point where it left off in the old TSS. So it is basically the TSS is basically related to this task. So the backlink information of this new task is related to this task, that is old task, and from here the task 5 will start executing. Okay, so up till now we have discussed task switching without task gate. So task switching happens without task gate if RPL is equal to CPL, but if RPL is greater than CPL, then task gate will come into picture. Whole thing will remain as it is, only task gate descriptors is coming into picture now. So here instruction is having selector and offset field with it. So the selector in the instruction will select the task gate descriptor from local descriptor table or interrupt descriptor table. If interrupt descriptor table, if any interrupt occur, then task gate descriptor from interrupt will get selected and so on. So here selector field will select the task gate descriptor. The task gate descriptor is also having, now this is the task gate descriptor, it is having the selector field and also the access right bytes. Okay, so the access right byte will be checked, and after the successful checking, the selector field inside the task gate descriptor will select the TSS descriptor from LDT or IDT. Okay, once the TSS descriptor get located, the fields inside the TSS descriptor, that is base field and limit field, will be copied into the invisible portion of the task register, and from that TSS will get located. So here the task gate, with the task gate we can switch from lower to higher privilege level. Here once again, if maximum of CPL and RPL is less than DPL of the task gate, then only then the current task is allowed to switch to the new task. Thus in this case task gate descriptor is used. Now we will see the task switching with task gate. So here firstly previous level will be checked. It is just like a previous. If maximum CPL and RPL is less than or equal to DPL, then task switching is allowed. So DPL of task get descriptor, here you should note that it is a task get descriptor. The DPL of task get descriptor is checked. Previously we used to check the DPL of TSS descriptor. Now here task get descriptors DPL will be checked. If this condition matches, then the switching is allowed. After successful check, then second stage is to check whether TSS descriptor of the new task is present or not. So task gate basically locates the TSS descriptor from LDT or IDT. So this TSS descriptor will be checked. whether it is present or not. If it is present and the task is not busy, then save the state of current task in current task TSS. So here current task TSS context are saved in the TSS of the current task. Then load the selector of new task in the task get descriptor. So here task get descriptor of the new task which has located is active now, and here load new task state in TSS, that is new TSS, and continue the execution. So here new task context are saved onto new TSS and the execution is then done. Now just before switching back to the old task, firstly it is checked new task TSS has old task TSS backlink. So new task TSS is having the backlink information of the new task TSS. So here what happens is this backlink information is automatically loaded into the task register. So this information will get loaded into the task register. So all TSS will get activated. So this will select the TSS and this TSS will get activated. Now this TSS is having the information related to the next task. And here from this information the next from the next task the execution will be done. So up till now we have seen the basics of multitasking, what happens during multitasking, how the task related management register, which is called as task management data structures, are coming into picture that we have seen. Now we will see the structure of all those descriptors. So let's get started with TSS descriptor. So here we have already discussed that the selector field of the task register selects the TSS descriptor and this TSS descriptor locates the TSS. The structure of this TSS descriptor is shown over here. The TSS is defined by the TSS descriptor. The selector is an index to a corresponding TSS descriptor that we have discussed right now. Each TSS descriptor is of 64 bits long, and here the first field of discussion is base address 0 to 15, then 16 to 23, and then 24 to 31, means total 0 to 31 it is 32-bit base address. It is called as 32-bit segment address also. This 32-bit base address of the segment is available in three different fields. During task reaching operation, the 80386 will add up the entire 32-bit address segment limit. It is divided into two locations. So 20-bit segment is available into two fields, that is 0 to 15 and 16 to 19, total 20 bits. It specifies the size of the segment. Then it comes the granularity bit. Now this bit indicates how the limit field is to be interpreted, that is how the limit field is to be specified in terms of its size in bytes or size in 4KB chunks. If this bit is set, then the segment size changes from 4KB to 4GB. If this bit is not set, then the limit field represents the segment size is from 1 byte to 1 MB. Means here if G bit is 1, then 4GB of memory will get accessed. If G bit is 0, then only 1 MB of memory will get accessed. The discussion related to this we have done in previous lectures. Then it comes available bit AVL. AVL, if the segment is available for the use, then this bit will set. If segment is not present, then this bit will remain 0. Then the second one more bit, that is P bit, present bit. It is called as segment present. If this bit is used to indicate whether the segment is actually present in the memory or not, then it comes DPL. DPL field means this bit indicates the privilege level of the segment and it is used in the protection checking. Then we're left up with this B bit, that is busy bit. This bit indicates the status of the task, that is it indicates whether the task is currently running or the task is waiting to run. Means is it busy or not, it's been indicated by this B bit. Okay students, now we will see task get descriptor. In textbook, task get is specified at some places. I will recommend you not to get confused with task get and task get descriptor. We will study task get descriptor only. So studying both the things are one of the same thing. Now we will see what is task get descriptor. A task get descriptor serves as an interface point between TSS and user code. TSS and the user code. It refers the TSS. So TSS descriptor basically points to the task get descriptor. Sorry, it points to TSS descriptor. So this is done with the help of selector field. The task get contains the selector of TSS of the new task as well as the access right bytes. So access right bytes is the DPL. It's 2 bits plus present bit and few more bits. DPL controls the right to the use to the descriptor to cause task switch. So DPL will be checked before task switching. P is the present bit, it indicates whether the TSS is present or not. So in this method of task switching, the task can be invoked indirectly by jumping or calling the task get. This method is used to transfer the control to the task at the RPL that is higher than the CPL. If task switching happens without task get, it means that RPL is equal to CPL. In case of task get descriptor, that if it is getting used, it means that RPL is greater than CPL. Okay students, we will stop here with this unit. After this we will see the interrupt and exception in case of 80386. Thank you all of you.